Welcome to the first ever webinar of the newly formed Carolinas section of the American Ceramic Society. I'm Jacob Jones, Professor of Material Science and Engineering at NC State and Chair of the Carolinas section. The first meeting of the section, just to give you a little bit of background, was in the fall in Winston-Salem. This was actually before we were formally a section. And tentatively, we decided to plan spring webinars like this one and fall in-person meetings. So the next fall in-person meeting, we're thinking of holding it at Clemson University, but the details of that are yet to be worked out. The attendees at the Winston-Salem meeting also expressed great interest in hosting the webinar during a lunchtime and including representatives from industry as well as academic circles. And so that's what we brought to you today, in a topically focused webinar on the topic of electronic ceramics. It's our hope that the recordings of these webinars will be made available on the web, perhaps linked through the Carolinas section website on the American Ceramic Society page. So without further ado, it's my pleasure to introduce our speakers for today's webinar, Veronica Augustyn, who's an assistant professor at NC State in Raleigh, and Craig Nies, senior technical staff at AVX Corporation in Fountain in South Carolina. And so they prepared some presentations that will last about 15 minutes. I hope you'll enjoy watching it while you're eating your lunch or otherwise enjoying some nice weather down here in the Southeast. So after the 15 minutes of presentations, we'll open it up for questions. You can submit questions through the chat box. I'll be looking at the questions and I can say them out loud to Veronica and to Craig, and they can respond. And then about halfway through the time period, we'll move to Craig's presentation, which is about 15 minutes, and then open it up for questions as well. So I'll stop sharing my screen, and hopefully Anna will let us transition to Professor Augustyn's screen.
Okay, hi everybody, this is Veronica Augustyn. Jacob and Anna, can you confirm that you see my screen?
Yeah, it looks great.
Okay, great. So I'm an assistant professor of material science and engineering here at NC State University. My research really focuses on the electrochemistry of materials, primarily transition metal oxides. And it's very nice to be able to share some of that work with you today. And I thank Jacob for the invitation. So a little bit about what my research group does. So we have several active projects. The main theme is really to design, synthesize, and then understand the fundamental mechanism. These focus on energy storage applications, where we're looking at things like ion transport in what are called solvated layered oxides. So these are metal oxide materials that incorporate structural water or other types of solvents inside. This theme is related to our other major thrust, which is to find energy storage that would enable simultaneous high power and high energy densities, because this is oftentimes closely coupled together, or decoupled rather, in electrochemical energy storage materials. And then we also are looking at how we would assemble these new materials that we're investigating into advanced electrode architectures. And what's shown at the bottom left-hand corner is an architecture based on a carbon nanotube foam material that has been coated with a molybdenum oxide. And then most recently, we're moving beyond looking at energy storage or redox reactions occurring on transition metal centers into things that could be happening within molecules confined between layers of things like oxides or transition metal chalcogenides. So first, I wanted to thank the folks that contributed to the work that I'm going to show. Two graduate students in particular from my group, James Mitchell and Ruotsun John Wang, as well as the work of a postdoctoral fellow that was with us for a few months, Elisa Patterson. I'll also talk about work through our collaborators, primarily at Oak Ridge National Lab, but also other institutions. And the work that I'm sharing with you was supported by the National Science Foundation for the Synthesis and Electrochemistry, and the AFM work was supported through the DOE FIRST EFRC. We also utilize user facilities supported by the Department of Energy, and I wanted to highlight this because it's an important component of our research these days. Okay, so what are the main takeaways from my presentation that I want to share with you? First is this concept that we've really been, I think, on the frontiers of, and that's to think about how to modify the interlayer of two-dimensional and layered materials to tune the electrochemical environment. And from a philosophical standpoint, what happens when that distinction between what is actually a liquid and what is solid is blurred under this extreme confinement? Then I'm going to talk about a very specific mechanism we've discovered in tungsten oxides, where we find that the presence of structural water leads to extremely fast proton intercalation, and how we used operando characterization tools to find that it's really related to the mechanical deformation that occurs in these materials and how structural water minimizes that. Thirdly, and this is something that will be pervasive through my presentation, is how critical it is for us to utilize operando techniques, so techniques where we're looking at how the materials are responding in real time in their electrochemical environment to understand energy storage materials, especially in situations like the one that I'll share with you where we are very, very far from equilibrium conditions. So why do we do the work? The big motivation is that coupled ion electron transport has very practical applications for our daily lives. The movement of ions and electrons in our batteries is why there's a finite time that it takes to charge our phones or to charge an electric vehicle. And we are living in really a unique time of human history where nearly every person is in daily contact with a lithium-ion battery, at least one lithium-ion battery, very, very closely intertwined with the portable electronics revolution. These are the number of mobile cellular subscriptions worldwide per 100 people. So you can see this very dramatic increase once the commercialization of the lithium-ion battery occurred in the early 1990s. And so recently in the fall of 2019, the discovery and development of lithium-ion batteries were rewarded with the Nobel Prize in Chemistry for creating a rechargeable world. And the mechanism, the fundamental way that these batteries work is through the process of electrochemical intercalation. When ions are shuttling back and forth between two different electrodes, the lithium ions are basically nestling into the vacant sites between layers of either a metal oxide material on the cathode or a carbon material at the anode. So high power electrochemical energy storage, we want to go faster and faster with these devices. There's a number of reasons why we want to do that. We want to have situations of fast discharging for things like communication or acceleration of a vehicle, but we also want to have fast charging. And the timescales that we're looking for are really things that can operate on minutes or seconds. These are timescales that are difficult to obtain with the lithium-ion batteries that we have around today for a number of reasons, but one of the major ones is just the diffusion kinetics inside the layered materials are slow. So what has been tried by the field is to nanostructure materials to decrease diffusion distances, and this works for virtually any intercalation type material. And this is an example of that lithium cobalt oxide that John Goodenough discovered. And if you have it in the bulk form, these are the closed circles here. The capacity as a function of the current density decreases much faster than when you nanostructure it. So this has been known for several decades. But the drawbacks why you don't see materials like that in the industry is that when you do this, you also increase the potential for side reactions with the electrolytes. These batteries operate not within a thermodynamic stability window of the electrolytes, so kinetically you're going to exacerbate that, and that's a safety problem. And the other major issue is that you have almost too much porosity and your volumetric energy density goes down. So nanostructuring is not necessarily the best way to go for intercalation type materials. A few years ago, Yuri Gogotsi and I wrote this perspective where we talked about a new type of materials that confined fluids within their layers, and how maybe by doing this, we can combine the benefits of what are called bulk layered oxides, the ones that are traditionally used in batteries today, with the benefits of nanostructured materials. And what we're doing here is we're tuning the interlayer to be no longer something that's vacant, but contains some kind of species that either opens it up or acts as an internal electrolyte. So we had these hypotheses that we could decrease interfacial charge transfer that occurs on the electrochemical reaction, and we could perhaps also have much faster ion diffusion through mechanisms that are more fluid-like, or simply more fast cell volume expansion because you have lower density structures. And so what our group's been doing is we've taken a look at this model material system based on tungsten oxide hydrates. And these are thermodynamically stable materials that you can readily synthesize at room temperature from a sodium tungstate salt. And if you do that, you get this dihydrate structure, which is a layered material of corner-sharing tungsten oxygen octahedra, separated by about 7 angstroms. And you have 2 types of water molecules: a lattice water that's just loosely bound within the interlayer, and a water of coordination that's actually directly coordinated to a tungsten. So these octahedra are highly distorted. If you heat this material up just at a low temperature, that lattice water is removed and you form the monohydrate structure. The water of coordination remains, and it's a little hidden here, that second hydrogen back here. At a much higher temperature, you can completely dehydrate the structure. And now what we have is a system where we can control the amount of water in the structure at low enough temperatures where we're not changing the surface area or morphology of our particles. And these are powdered materials upon synthesis. All 3 of these phases are electrochemically active, meaning that they will intercalate a variety of cations from the electrolyte. All of them are based on the redox of tungsten 6+ to tungsten 5+. So that's all staying the same too. And for our purposes today, I'm going to talk about our work with proton intercalation. And what's fascinating, what we discovered, is that when we have these hydrated tungsten oxides, we can see sub-second proton intercalation kinetics. And this is really incredible for an electrochemical energy storage material. Typically, the timescales that are measured for high-rate energy storage materials are 10 or 15 minutes. So here we're talking about fractions of seconds. And these are cyclic voltammetry curves where we're comparing the 3 different phases: the anhydrous tungsten oxide, and then the hydrated ones. And what you see, the reason why I say we have this really exciting performance, is that the area enclosed by the hydrated phases is higher, meaning that you have a higher specific capacity. And this behavior is true for all of the scan rates we investigated, and here these were particularly fast. Also, the electrochemical reversibility is very high, meaning that the energy efficiency of this electrode would be high. So when we wanted to understand why this was happening, we wanted to take a look at how electrochemical redox affects the bond length changes. And if you have a very simple molecule like ferrocene, when it's oxidized, it will have a lengthening of its iron-carbon bonds by about 0.1 angstroms. So then imagine if this happens to an intercalation electrode like the one before, you have all of these tungsten cations accepting electrons, you have cations and protons coming in. The material is going to expand in volume. And so measuring that rate could provide additional understanding of electrochemical intercalation kinetics. And this is where our collaboration with Oak Ridge National Lab came in. They have the setup to do this operando atomic force microscopy, where we're going to link the kinetics of the intercalation that we measure from things like cyclic voltammetry with the mechanical deformation of the material. And this is how the electrochemical cell looks like. And what we're doing is, this is now topographic images of our oxide electrodes, is we're going to take the AFM tip and place it on top of our material, and then just watch the deflection of that AFM tip as protons cycle in and out. And these are the cyclic voltammetry curves from this particular cell. So what we're measuring is the electrochemical current through this electrochemical cell that's coming from everything on the electrode, as well as the very local deformation from the nanoscale tip that's coming from this operando AFM result. And what's really exciting is that we saw when we had the hydrated structure, it had much more reversible and smaller structural deformation. So the deformation magnitude was lower when we had water in the structure versus when we didn't. But also this hysteresis was much smaller, almost non-existent, meaning that the reversibility of proton intercalation, deintercalation was much higher. There was also this very interesting lack of sweep rate dependence. So we don't see any differences on the deformation, no matter how quickly we scan between the potentials, whereas for the anhydrous material, we do. And when we coupled this result with operando X-ray diffraction, this was now done at the SSRL, the Stanford Synchrotron Radiation Light Source, we found that what we were observing in the AFM was really the fact that the hydrated material exhibits a much faster electrochemically induced phase change. So these are now operando X-ray diffraction results. There's a lot of information in these figures, but we're plotting time along this y-axis. On the left-hand side in this green panel is basically a contour plot of the X-ray diffraction pattern. And on the right-hand side is the electrochemical input and the current that we're measuring from the material. So we're really measuring this in real time at charge-discharge times of 70 seconds. For the hydrated material, we see this beautiful reversible phase transition that takes place as a function of proton intercalation. Whereas in the case of the anhydrous material, you see that it never completely transforms into its protonated phase in the time scale that we're investigating. If we push the materials faster to 100 millivolts per second, now we're going to a 7-second charge discharge time, that hydrated material is still able to keep up with that phase transformation, whereas the anhydrous one essentially appears frozen. And this is directly tied in to the capacity that we obtain from both of these materials at the very fast rates that we're interested in. So to summarize, I wanted to share with you this concept of how we can tune the interlayer of materials and how that can affect electrochemical behavior, in this case, energy storage processes. A particular mechanism that we've discovered in these tungsten oxides, where the presence of the structural water is really about minimizing kinetics and enabling very quick phase transformations to take place. And then the importance of studying these materials using operando techniques. In this case, we had both the AFM as well as the X-ray diffraction to bring us the full story. And with that, I'm happy to take any questions you may have.
Great. Thank you very much, Veronica. And so for anyone that joined late, we're taking questions via the chat box, and then we'll repeat those here for Veronica to hear and for everyone to hear the answer. And just to get us started, I'll go ahead and ask one. I was reading the Science magazine, I think the most recent one or the one before, it was end of January, Veronica, and there was a 2-page opinion piece called Rethinking Chemistry for a Circular Economy. I was just wondering if there's discussion in the battery community about the circular economy as it relates to some of these metals and the ability to recycle some of the materials that are being pursued.
Right, yeah, that's a very important topic, especially when these lithium-ion batteries, which are the dominant chemistry right now, when these lithium-ion batteries are going to be used for larger and larger applications, particularly in transportation. So in that, when that scale is going to increase, and it's definitely coming, then you really need to think about battery recycling. My research group, we don't really focus on this topic, but I know that the Department of Energy does pay attention to this. There's a group at Argonne National Laboratory that has really looked into this at length and made all the economics calculations about what should be recycled, what's the most energy intensive process, and so forth. From my understanding, one of the challenges for lithium-ion batteries, unlike something like lead-acid batteries, for example, that are recycled routinely, is that the chemistry of lithium-ion batteries, even though it's all kind of the same, it's also slightly different. So some of the cathode materials contain more cobalt, some of them contain more manganese, some might contain a little bit of silicon. And so that diversity of the battery shape, size, and then the internal chemistry affects how easy it is to recycle them, to find large scalable processes. But I think this is where, when you go towards large penetration of electric vehicles, there will probably be more uniformity and more scale to make this much more widespread.
Okay, great. Thank you. So one more question then, which relates to the capabilities. So you show a lot of characterization tools. Given that this is a Carolinas section, which of these tools, if any, are available to anyone watching this webinar? Are there any that are publicly available? Publicly available.
So I didn't show, we extensively use the AIF, the Analytical Instrumentation Facility at NC State. And I do want to show some of these results. So for example, taking cryo-TEM images like the one here in the upper left-hand corner, that can be done at AIF. The bottom left-hand corner is actually the micro CT that we just received at AIF. And this is something that I didn't think our group would be using, but we're actually using it now to understand these electrode architectures. So the top part of the image is a cross-section of the electrode, and the green, horizontal green line is showing you this slice that you see here. And in the case of the electrode architectures, where we're not interested on the atomic scale organization, but really like the long range arrangements, this is a beautiful technique to use. So use AIF routinely, and those are publicly available. The operando results that I show, those techniques are all through user proposals to Department of Energy facilities. And I think those are also welcome industry proposals.
Okay, great. So thank you very much, Veronica. We very much appreciate your presentation. And I think what we're going to do now is move to South Carolina to the industrial presentation by Craig Nies. So I believe Anna is online, and she's going to give control to Craig, or Craig's going to take control by sharing his screen. It looks like Craig.
Hello there.
Yeah.
Can everybody hear me now?
Yeah, we can hear you.
Beautiful. Okay.
I introduced you briefly at the beginning.
Excellent. Sorry for the delay there. I believe I had an entrance problem. I must have tried to come in through another route rather than the route that we had practiced, and that gave us some difficulties. There we are now. Hopefully everyone can see my duplicated screen here.
Well, we're seeing the presenter. There we go. Perfect.
There we go. All right. Nothing forward here. Let me just briefly introduce myself again. I'm Craig Nies. I'm a PhD senior member of technical staff with the Advanced Products and Technology Center at AVX. We have been in the business of electronic devices now for almost 50 years when it comes right down to it. I've been here for about 30 myself. The AVX had originally started as AVX Corporation, and sometime back in the distant past, the board level portion of AVX went its own way under the AVX name, and we became AVX. So that's our position in time right now. Just moving along here, I want to give you a quick outline of what we'll be talking about today. All I got to do is figure out how to get that to happen. There we go. By way of an outline, I want to tell you a little bit more about AVX and the kind of things we do, but then focus on AVX and the ceramic devices that we produce. I want to talk a little bit about key trends in ceramic device construction, and then focus in on X7R materials and voltage tunable capacitors. That's sort of a novel concept that we think might have some interest as time goes on here. So this is just an overview. AVX is a leading international manufacturer, supplier of electronic components. We have 29 manufacturing facilities in 16 countries around the world right now. We offer a broad range of devices, including capacitors, resistors, filters, couplers, sensors, all sorts of devices that we actually are part of the AVX product line. We like the fact that we can be a one-stop shop when you have a number of different electronic items that you might need to construct circuits. Our global footprint looks a little like this. Our corporate headquarters, as Jacob mentioned, is in Greenville, South Carolina. We have several U.S. facilities, but we also have several European facilities and locations in the Far East as well. Right now, our headcount is someplace over 15,000 employees, and last year's the FY19 sales we had were about $1.8 billion overall. We'd like to think that we do offer by our economy of scale that we can also do a number of reasonably priced devices, but in fact one of our favorite things to work on, if you will, are more advanced products that address the up-and-coming needs of the electronic community. We can talk about the marketplaces at AVX Services, and in many ways we've got a footprint in most of them. Our largest market share is in automotive currently, and that's due to the fact that in the past few years we actually acquired a sensor company that has a large footprint there too, which nearly doubled our scale. So that's our group in AB, which is now a AVX Group company. But we also have large activities in the industrial, in the telecommunications market, and in the consumer markets. And our fractions are somewhat smaller in the medical, defense, aerospace, and other specialized markets. But we treasure those markets because they tend to be high ASP, and they do keep us on the cutting edge and keep us moving forward. You can see AVX does have a number of other brands, including AB, that are part of the AVX portfolio. We see the growing markets in the world and the things that we do try to pursue with great veracity. Again, automotive electronics, as everyone knows, is exploding right now, and so we are very much attuned to what the manufacturers are requesting in terms of those devices. Mobile and telecom, and in some ways are becoming sort of related, those two marketplaces, as we all move mobile communications and also mobile computing to our cars. The advanced areas of medical and aerospace are examples of markets where we feel that there will be an amazing amount of growth in the future, but it also represents those high-end, high reliability aspects, which are very much demanding and require a component manufacturer to really be on their toes, both in performance and in the reliability of the device. From this it shows a broad look at AVX product portfolio right now, and you can see we have a number of types of devices that are represented here, including a number of different capacitors, which are probably make up some of the larger portion of our devices or our traditional market. But you can also see that we do have a big footprint in interconnect devices and sensing devices now, thanks to some recent acquisitions. And one particular thing that has added to our product line has been antenna functions, and that's our Ethertronics group. So we do have a wider variety than the traditional passive components that AVX has previously exhibited. And we're happy to have those things, and we hope to move forward in the area of modules and other sorts of devices that take into account assemblages of the many products that we sell. What I'd like to do just for a moment is focus on some of the ceramic devices that we do make, and focus on the kinds of things that those are apparent. First of all, there are traditional ceramic capacitors, which are kind of shown in the far left here. That includes not only the traditional sort of rectangular sorts of footprints that may either be surface mount device or lead frame devices, but we also have a variety of discoidal ceramics that are used in some fairly high performance connector devices. And also we do have traditional leaded devices that are still parts of our portfolio. Some of the major materials that are used in those are barium titanate, neodymium doped barium titanates, and more recently, as we improve and expand lines of base metal type devices, which we can talk about a little bit later, the SCZT family of materials, which allows copious use of base metal in very flat TC NPO type devices. Next in line, I've noted circuit protection devices we make. Those include varistors, which are both made in disc and multi-layer formats, and also thermistors, and families of ceramics that typically appear in those would be zinc oxide base for the varistor materials, and transition metal compositions of oxides that are used to form the thermistor lines that we have. Following that, in high frequency ceramics, we have a variety of both high Q capacitors, inductors, again, some high frequency varistors, and also single layer capacitor devices that take a variety of simple and pattern formats. Typical materials that might show up in those, again, would be some of the neodymium doped barium titanates, but also some of the higher titanates, which do not have the same kind of ferroelectric performance as some of those used in the traditional ceramic capacitors, and also calcium and magnesium titanate materials. And then finally, we do have thin film lines that are used for making advanced products and advanced arrays of passive components. Traditional materials we'd be using those would be standard SiO2, silicon nitride. Combinations of those materials can make some very flat, tight tolerance capacitors. Resistors are often made with tantalum nitride. We also do a variety of metallizations that can be used to make inductors and other forms of these devices as well too. What I've tried to do is list the base materials that are common to our products, but common additives would include P or N-type dopants. As you might recognize, most of the materials we have here are defect semiconductors, and their properties can be improved using those kinds of strategies. These are traditionally done with transition metal or rare earth oxides. We also introduce a variety of fluxes which can help control sintering, and also some grain growth controlling things. One of my favorites there is manganese oxide, which is famous for helping grain size control in barium titanate. Just to look at the schematic of a basic multi-layer device, this would be common not only for multi-layer ceramic capacitors, but also other novel devices. The multi-layer varistor or transguard materials are a fairly common product, and we look to expand those to other versions of circuit protection and other advanced devices too. The pictures here kind of show the major pieces of what those devices would be comprised of. You can see here the active area in a device is where we have alternating electrodes plus the ceramic track between those two materials, where the functional operation of the device goes on. So you can see the material in the lower picture here shows a quite dense layer where we try to get as many layers as possible into a device, and a close-up of that is shown on the left hand, where we can see having electrodes that are on the order of magnitude of the actual electrode thickness, dielectric layers that are on the order of magnitude of the electrode layers here. So something in the vicinity of 2 microns for the dielectric, and then ranging from 1 to 2 in the electrode portions as well. Our internal electrodes traditionally were made of precious metals such as silver, palladium, platinum, and palladium itself. More recently, probably the past 2 decades, has seen a great climb in nickel and copper, and the bulk of the consumer grade parts, and often some of the more high performance devices are actually being used or made from those materials right now. But there is a significant difference still in precious metal parts, and there is a business available for those devices too. In order to make a connection between these, the ceramic device and the outside world, some type of termination is used. This is where we make that electrical contact. It usually consists of a dipped Cermet type product. Often that is based on either silver in the case of precious metal electrodes, or copper in the case of base metal materials. Often both of those materials as the base would require some sort of plating overcoat. So we use a combination of nickel and tin in most devices, and you can see the kind of combination. The nickel acts as a barrier which prevents dissolution of the base material into any soldering that happens, and then the tin provides an oxide barrier or a prevention of the nickel from actually being oxidized, and so we coat that with tin. That's also a very wettable surface that works most well in most soldering operations. The materials are all surrounded by some sort of a cover layer or margin kind of structure. And the reason I actually point that out as a fairly different material here is, first of all, it does perform some fairly significant functions. And first of all, that provides the bulk of the insulation with the outside world. So any contact with the outside world is prevented by those layers, but also environmental protection, and that would go along the same kind of line there, both electrical and environmental. I think one thing to point out, though, is because of the proximity of these, the fine electrodes that we have, there's a good bit of stress concentration in the margin regions of the part. And there's also good, fairly hefty mechanical stresses if you think of the differences in shrinkage perhaps between the outside and the inside of the device. So we take care to manage all those kinds of things which are part of constructing an MLCC. I'd like to just talk, I started my career here in 1988, and so I've had a chance to look at some fairly significant changes in the world of devices. And this actually leans more toward the capacitor world, but in fact, these statements could apply to anybody making a multi-layer device of any composite nature. And the first thing that is an important change is the minimum device footprint. When I first joined AVX back in 1988 and toward 1990, I would say the smallest device that we tended to work with was something that was what we call an 0805, that was 80 or about a 32nd of an inch long by about half of that wide. And just recently we saw that there's work in the Far East that shows we've actually dropped that for devices. The state of the art is actually an order of magnitude lower in both dimensions on that. Now obviously that does imply some reduction in the voltage that would be applied to these devices, but you can see the sense of extreme miniaturization that is available from multi-layer ceramic devices these days, and I think that's pretty impressive. Ceramic layers are concomitantly smaller. Back in the day, you might say that the 18 microns was one of the thinner fired layer that you'd see, but now 1 micron is fairly common, and people are reaching below that thickness. And this has given us higher volumetric efficiency and reduced voltages. The minimum ceramic grain sizes in those days was someplace near 1 micron, but today a more common dimension is something in the nanoparticle range, 50 to 150 nanometers. And this has allowed improved reliability and important voltage performance, and has allowed thinner layers, which has again pushed the volumetric efficiency of the devices. Electrode materials have gone from the precious metal combinations that I described before down to base metal materials, and cost is the major driver in those cases. However, once we found out that we found that nickel devices actually enabled us to go to thinner ceramic layers, as the interactions between palladium, which was typical of the electrodes of the days, and the oxidation that would occur on those and then be released throughout some of the heat ramping sections, the firing profiles, actually caused some disruptions in the thin dielectric layers. And so nickels did not go through a lot of those changes, and therefore allowed a more stable thin layer device. And lastly, terminations. I described the termination materials that are standard up here, but what is still a staple of the industry is really a dip termination. That's a cermet that's applied in a thick film fashion. However, in the past decade, there's been a rise of all plated terminations on devices, where electroless plating can be used to lay down base layers, and followed by plated regions that match those. And this has allowed for some tight terminal geometries and multiple regions of termination across each surface of the device. So that's actually, although not really ceramic related, has done as much for advancing the case of these types of devices as almost any development. So now I'd like to talk about a specific case. It's one that I've spent some time working on, but it's also indicates the importance of understanding not only the chemistry of a device, but also the microstructural performance of the device or characteristics of the device that lead to its performances. And so I'm going to talk a little bit about what we call X7R devices, and I'm not really certain of the composition of the audience here, so I did include a quick description. X7R devices probably still make up on the order of 70% of the capacitors that the ceramic capacitor business, and they actually kind of vary into two groups, X7R and X5R. They're very similar devices, but the X7R range implies a temperature control of plus and minus 15% of the room temperature value over the range of minus 55 to 125 degrees C. So that's a reasonably flat capacitance value over that range. The remainder of the market is largely made up of what we call NPO devices, which have far less than 1% over that range. So those are used in much more stringent environments, and their value tends to be lower. X5R capacitors exhibit some of the similar properties, but their range is limited to 85 degrees C. And many devices that are X7R meet this temperature range actually implies a reliability of the device too, up to 125 versus 85. But many X5Rs will actually meet the 125 degrees C reliability specification as well. So the idea is to keep in mind that these devices have taken the bulk capacitance market up in a large case. And so that's why they're significant. And they are based on barium titanate. I've borrowed a diagram of a ferroelectric hysteresis loop from my favorite reference from the old days, and that's from Kingery's Introduction to Ceramics here. And you can see that the relationship between both the polarization and therefore the dielectric constant of a device actually changes with the field. The slope of the PE curve is actually what's represented as the dielectric constant. So when we apply a field to the device, we can actually see that the slope of that line changes as we march along it. And the K is actually, if we were to put bias on the device, we would actually move that slope along this line that's represented in the upper right-hand quadrant. So you can see one red arrow has a certain slope, a relatively high slope at low bias fields, but up at higher bias fields, it gets a relatively low slope at that point. And so having a higher slope down here, low slope, means that the dielectric constant actually falls over that range too. And so as we start thinking of devices for higher voltages, we have to understand that there will be some roll-off in the properties. Typically, larger grain size materials show larger effects of this type of change in dielectric constants. And so this transition occurs or begins to show up in the material, for example, in barium titanate at its Curie temperature of 125 degrees. So in order to make that material an X7R, a large peak occurs at that point, and what is necessary is to add dopants to actually flatten that curve out at that point. And so that's where the compositional work of making an X7R device comes from. This shows a little bit about the types of the changes in barium titanate that have been used over the years for X7R materials. Actually, there's a previous stage, probably maybe 30 years ago to 20 years ago, where we might have used something on the order of 1 micron down to 1/2 micron in grain size. But as layers got thinner, we found that we needed to gradually march down the grain size until you see the kinds of materials that are being used today at 0.1 micron. And the dielectric constant, unfortunately, tends to decrease over this range. And so, but it does allow you to make thinner layers. And so you're constantly trying to modify the material to keep the highest K as possible. But going to make thinner layers of material has ultimately turned out to be the best way to increase the volumetric efficiency of the material. And so there's still a large drive for the use of 0.2 and 0.1 micron materials, even though they can be challenging. Microstructure in X7R materials looks a little bit like this. They follow what we call the core shell model, if you will. And what that means is usually we have a high purity grain of material that is surrounded by a sort of a melange of dopants, if you will, that sit here. And although it looks like they form a grain boundary phase, what that actually represents is the outer layers of the grain that tend to dope, and they create a composite structure right within the grain itself. There's relatively little on the grain boundaries that are important to this discussion. And as you can see, with smaller grains, we might have more of that material present, or we might have the same amount of material distributed over different area. And so the amounts of dopants can be very important that we use in these things. Now, as we begin to start consolidating and firing this material, we can start with a fairly tight region in the grain boundaries of a range or a spatial distribution of the dopant materials. But as we heat the material up, that material can diffuse and create a much wider grain boundary or core or shell region, and leaving less and less of the core behind. And if we let that diffusion process continue, we can actually diffuse those elements right through the grain. And at some point, we'll actually lose control of the grain size, because the grain boundary dopants that were out there that were meant to control grain size all of a sudden are now incorporating the grain, and grains can grow from that position. And so all of a sudden, that causes an increase in grain size, which makes us lose control of all the temperature and voltage coefficients that we were looking for. So the important things to notice here is, as we diffuse more material in here, the material that's in the shell region becomes broad, and that material can impart temperature and voltage behaviors that are not desirable. So in many cases, it's important to have a tight grain boundary of materials if possible. The next slides will kind of illustrate how that process goes along. If we look at the temperature behavior now over what we described as the X7R range from -55 to 125 degrees C, we can see that using large grain materials where we have a fairly safe core, we have relatively flat changes in K versus temperature. But as we start to decrease the grain size of the material, we can get a very peaky look to the material getting down, and that's because that diffusion is taking place. If we were then to augment that with a little bit of sintering, all of a sudden we can see that we start seeing an expression of the Curie point now shifted because the material is doped. And so all of a sudden we lose control of the desired flat nature of the TC that we would like to see. And so this is one of the cruxes of what's necessary to control these kinds of performances when doing a ceramic formulation like this. Certainly, one thing we have discovered over the years is that the quality of the barium titanate that you use can have a big impact on this kind of behavior. Materials that have very fine or very high crystallinity, in other words, no disordered material that tends to be on the outside of the grain, tend to give us the best results in this way. Let's see here. We can also look and see the same kind of changes in the voltage coefficient. If we look through these materials here, we can see that the steepness of this curve tells us it tells us something about the voltage coefficient of the material. A steeper curve will have more change with voltage than will a shallower curve here. And you can see that some of the largest grain materials, as we might have pointed out, do have the largest change in retained capacitance or dielectric constant with biasing field. Now, given that a lot of materials are used out in the vicinity of 5 to 10 volts per micron these days in various applications, you can see that a material that can be chosen that has a much better, we can nearly double the retained capacitance in a device by looking at, say, for example, at 6 volts a micron and looking at the 0.4 micron curve versus the 0.3 and the 0.2 curve there. So that's an important change. And we can also observe the same thing if we watch the material for the 0.2 micron material. If we tend to fire that material higher and cause the diffusion to take place, we can see that the voltage coefficient of that material tends to become large as we get that peaky behavior that's undesirable as well. So the interesting thing is while we're busy trying to control these behaviors, somebody asked the question, is there a way to use this? Can we control the material? And what it means is that by using a biasing field on the device, we can actually tune the capacitance of the material to actually exhibit the dielectric constant that's required. And by actively tuning it, we can hold the value of the capacitor through a variety of conditions in both voltage and temperature. So a while ago, we embarked on a program where we actually were able to demonstrate different materials that had a variety of different voltage coefficients and therefore different applications. So we can see we had a Gen 1 material, which we call, and I'm referring to the right-hand graph here, where we actually had an X7R material and looked at its typical behavior. We found it to be a little bit steep in terms of voltage coefficient, and the material was somewhat lossy too. So a new composition was derived, and you can see that it has much lower slope to the voltage coefficient. But if you refer to the graph on the left, you can see that the dissipation factor, which is the smaller curve here, although the K of that material is smaller, the dissipation factor is much lower, and yet we can still get some tunability out of that material. On the other hand, a Gen 3 type material, which has a larger composition of more diffusion of the dopants throughout the material, you can see it exhibits a much steeper curve. This material would require less tuning voltage to take place, although the losses might tend to be a little bit higher depending on the temperature at which you use it. So there are challenges in using any one of these materials. The biggest thing is being able to control both, not only controlling the voltage coefficient, but both the losses and the temperature behavior of the material too. Based on these types of materials, we also conceived some devices that took advantage of this design. And you can see by combining a set of active electrodes, which look like the standard electrodes that would appear in a device, with a set of biasing electrodes, adding a set of terminals to the outside of the device, we were able to create multi-terminal devices, as you can see, that actually allow you to separate the function of the bias voltage from the signal, which would probably be most applied on the transverse or along the length direction of the device. So what this does is it allows someone to actually apply a biasing voltage without making a complex signal which has a bias applied to it, which must be separated out later. And we made this in a couple of different formats. On the right side, you can see what's called the 1206, about 1/8 of an inch by 1/16 of an inch long device. We actually constructed some prototypes of stacked capacitors that could use this kind of characteristic for higher voltage applications. And we also made a very small 0402 device using plated termination technology that allows us to make a small form footprint device out of this material too. So we have these technologies available. The trick is that because these don't exist in the marketplace in any big way, there's not a lot that no one's conceived of the perfect application for them. So I think in some ways we're looking for that killer app for this. But in the meantime, we'll be studying this to see if the product becomes viable from that point of view. I just wanted to close with a statement that miniaturization drives all aspects of electronics today. You guys are familiar with all these kinds of things. Computing and wireless communication, transportation, and healthcare are all the hottest topics, and we all want our electronics to be more portable, more reliable, and almost more transparent to our lifestyle in a lot of ways, and that's how we achieve that. The materials community over the years has responded with a number of high purity materials, the sizes that have reduced, have really enabled the processing by coming down an order of magnitude and dimension, have allowed numerous new processes to be used. And also that's helped to usher in a new wave of these products that'll hopefully meet the demands of today's electronics market. And God willing, AVX will be part of all of that. Thanks very much for your time today.
Thank you, Craig. That was great. So for anyone that's joined as an attendee, you're welcome to input a question on the webinar chat box. I'll start us off, Craig, by saying it's really interesting to see for the X7R composition dielectric constants ranging from 1300 to 2700
Yeah.
By just
by the way, I would point out those were test devices that we make in the laboratory with relatively thick layers.
Yeah.
An interesting thing happens in barium titanate where we have you can get an enhancement of the field typically at the cost of the temperature profile, but there are X7R materials that will have dielectric constants upwards of 4,000 actually.
Yeah. Well, the interesting thing that I noted on your plot there for those test materials was that it's just a change of firing temperature by 30 degrees. 30 degrees change in firing temperature changes the dielectric constant by over 1,000. So I mean, the knobs to play with the microstructure and the resulting properties are pretty extraordinary.
Yeah, that's very true. One of the things that we do have to kind of cope with is the notion that if we're going to work with fine materials, the notion that the diffusion distances are much smaller and can distort the properties pretty quickly is something we have to kind of get a handle on. And again, the materials community has responded, though. These materials that have higher crystallinity actually exhibit greater stability and actually work to open up that firing window to a great extent.
Yeah. So do you focus a lot on the processing property relations, or do you also dig into the structure property relations, for example, by looking at the microstructures in TEM or perhaps getting EDS profiles across the grain boundaries?
You know, it's interesting. The fact is that we came to a point there where you could, we do, first of all, we do those things. We do look at the X-ray diffraction patterns, although it's a relatively coarse measurement at these kind of scales. EDS and SEM have been important tools, and they've given way to a lot of TEM work that allows us to understand the grain boundaries to some extent, and that diffuse layer that we have. But you know, the interesting thing is that in the end, a quicker and somewhat more definitive route is to actually be able to interpret the temperature envelope curve that I described there. One can almost from that make decisions on the firing process without having to look too hard at the microstructural basis for some of those changes.
Yeah.
However, it's never good to just trust the electronics. It's a good idea to go in there and confirm what you believe at any point. So that's still part of our discipline.
Yeah. Okay. Well, that's great. I think we're almost out of time, and I don't see any more questions coming in the chat box. So I'd like to thank Craig and Veronica again. And like I said at the beginning, it's our goal to have these recorded and posted online after the fact so that folks that couldn't dial in during this lunch hour would be able to see the remarkable work going on in the Carolinas on the topic of electronic ceramics. So thank you all for attending, and hope you have a great day.
Thank you.